Last but not least, we'll hear from Bluespace AI.
Future of autonomous vehicles is coming, but with a cost. According to a RAND Corporation report, it would take 8.8 billion miles to demonstrate equal reliability of an autonomous vehicle to the reliability of a human driver. Not only are we nowhere close to that 8.8 billion miles, the reality is pretty grim. As we read in the media, horrible crashes on the highway and another senseless fatality after another with a careless mistake. While the future with autonomy is very promising, accidents by robots are happening, and it's costing us capital, time, and our lives. Now, we don't want these accidents to happen in space, let alone Earth. While we try to perfect perception and prediction in the AV stack in many different ways, driving millions of miles, for example, having human in the loop with remote monitoring. In space, all these options, driving millions of miles or relying on mapping data, presents additional challenges. Furthermore, the need for lower latency, lower compute power, and the limited budget, and the challenges of mapping are all exponentially even more challenging in space. Hi, I'm Christine Moon, co-founder and president of Bluespace.ai. We're a software company based out of Santa Clara, California. We are using the latest Gen 4D sensors to enable perception for all autonomy here on Earth and in space. Bluespace brings together a team of AV veterans who've worked at global OEMs, world-class research institutions, and leading autonomous vehicle software tech companies. Bluespace's breakthrough is twofold. First, it's the theory, the discovery and the derivation of the relationship between objects' true motion and the observed sensor data, enabled by the latest sensors such as the FMCW LiDARs or imaging radars. As we have seen in the past, new insights allow for new capabilities. Bluespace's theory, which is the first breakthrough, allows for us to build perception software for all autonomy, which is the second breakthrough. Similar to the discovery of E equals mc squared, while in theory it's explaining the energy released in an atomic bomb, it does not explain how to build one. And that's the second breakthrough of Bluespace, where we have built the robust and generalizable perception software stack to put our theory into practice. And we believe that this will enable and accelerate a safer and scalable path to commercializing autonomy. Autonomy is already all around us, and we will continue to see more AVs in ride-hailing, delivery robots, or AV trucks here on Earth. Autonomous hauling trucks have been used in mining for decades. Robotic combat vehicles and military has also been deployed. And NASA is no stranger to developing autonomy. As an example, let's talk about the tale of twin rovers Spirit and Opportunity that were sent to Mars simultaneously. As you can see, one had a lifespan of 14 years, and the other, Spirit, had less than half of that. And you can see how productive one was in providing raw images, while the other one was less than half of that. So what happened? Well, as you know, Mars rover exploration has many critical tasks, but as the tale of twin rovers tells it all, when one of them got stuck in a terrain where it was not familiar with and couldn't get out, it prematurely ended its mission. Other examples are where there's growing congestion in outer space. So the fact that precision in perception and being able to predict the motions of the object around us can be applicable to space is very, very close in the near term. There are three key values that Bluespace brings to the industry. First, it's the reduced latency. Traditionally, an AV takes snapshots of the environment over many different frames, one to classify objects, then to determine the movement surrounding the vehicle, and to infer where moving objects will go. This will be key input for the vehicle to navigate safely. Bluespace does not infer but measures all current velocities with accuracy instantaneously in one frame. This allows for reduced latency, and that means we can react faster to all scenarios. Value 2, less power hungry. Taking multiple snapshots and processing this data traditionally takes lots of power. Many compute chips on top of the CPU, such as the AI chip and GPU. Bluespace takes a leaner and smarter software approach. Therefore, we do not need as much processing power for autonomous operations. Third value would be removing the need for classification and thus reducing external dependency. Because we instantaneously compute the motion of the objects rather than inferring based on classification, we can handle endless edge cases, or the long tail of small problems, as Elon Musk calls it. Inference only works for use cases that the training data set was collected for, and the vehicle would have to continue collecting and training indefinitely to maintain an accurate performance and not cause accidents. And this has turned out to be an insurmountable task that's endlessly using capital and time to do and to perfect. That's why Bluespace's approach, having a generalizable solution to endless cases, allows us to scale faster to new environments and be able to have the confidence that we will not cause harm. The total addressable market is large, both on Earth and in space, and on and off-road applications. That said, we do anticipate faster adoption in the enterprise commercial space, and the consumer space will follow. The commercial AV market includes industrial, defense, mining, indoor warehouse, etc. Now, let's take a look at our software. Remember, it doesn't matter the computer has never seen the object before. It doesn't matter there are no lane markings in the terrain. It does not matter that we don't have mapping data to support our software. So in the video clips of our software, you'll see that our software, number one, detects the vehicle, the pedestrian, the scooter, or the pedestrian wearing boxes. And then furthermore, it's able to predict the motions of the objects as well, thus allowing for the vehicle to navigate safely. These are just prompters. Oftentimes our customers will bring relevant examples to test for the scenarios they care about, and thinking about how this software can really enable them to scale their operations. So anything in our field of view, we will detect and measure the true motion of that object. Now, that's scalability. No prior training needed, no reliance on mapping. Our commercialization path with our patented technology starts with our early access platform. Through our early access platform, our customers get to test our software firsthand. So instead of spinning up a team of 30 PhDs, they can take our early access platform to see the power of our perception system that will give the motion certainty and be able to operate in new environments. This perception in a box is a pre-calibrated sensor hardware and our software on top of low-power automotive-grade embedded SoC in a single unit. There is a minimal integration effort for our partner. Only power supply is required for our early access platform, and no data is needed from the customer's vehicle to Bluespace's platform. We have patented our technology in the US and internationally. For the next 12 months, we will have proof of concepts and NREs, and that will convert in the following years to licensing our technology. You can see that the range of our revenue and the projections can vary depending on the number of partners. What's interesting to note is that the profit margin starts in single digits, but quickly ramping up to upper double digits in the 4-year horizon. In 2019, we raised a seed round of $3.5 million. Currently, we're in the midst of raising our next round of financing. This is to really grow the team so that we can engage with partners globally. Autonomy will transform how we work and move here on Earth and out in space. We'll be able to expand our boundaries of where we explore to increase the safety of our personnel and vehicles, and to further aid missions of NASA. Bluespace provides the safer, scalable solution to harness autonomy for all missions. We provide perception without compromise, because you and your mission should not be compromised. Thank you.
All right, thank you very much. So do we have questions for Bluespace? Chandra, go ahead.
I have a couple. So I assume you're using LiDAR and sensors. Is that correct? Okay.
That's correct.
So my first question is how you can measure velocities in a scene in a single frame. My second one is how long into the future is the prediction and how is the accuracy in respect to that time? How many frames do you need to generate that prediction?
Hi, this is Joel from Bluespace. Happy to answer the questions. So one is that we're using next generation sensors. So these are 4D sensors. So they provide both the positional information like you'd get from your traditional time of flight LiDAR, but also a measurement of the radial velocity, so the Doppler shift on a point by point basis. So that's how we get that additional bit of information, but it's our software that's able to interpret all of that to provide a full, motion estimate for all objects. And for the second question, we do this on a single frame, so we don't need prior frames to get our first estimate of the object's motion, since that single frame information is enough. And the validity of the future prediction is really only bounded by the expected accelerations of the objects in the scene.
So to clarify, so you're not reading it from a single frame, it's the sensors reading over a short period of time.
It is a single frame, but the sensor each point that's going out, instead of just measuring the time of flight and getting you that radial distance, it also measures the Doppler shift of that signal. So it gives you that instantaneous radial distance and radial velocity. So that only gives one portion of the motion information, but it's a software that's able to reconstruct the full motion of the system.
Okay, thank you.
All right, great. Rich.
Great presentation. I can't tell you that I totally understand everything about the way you've developed your software. I guess the question from the business standpoint, this is a very crowded arena right now in sensor development. What makes you stand out? What makes you different? What makes you confident that you can take this and beat all the others?
That's very true. It's a very crowded market. And that's really where traditional approach of using 3D sensors, using deep learning based approach has been overcrowded. And you see the market consolidation. What we're doing is actually a new approach that is not crowded at all. There is a little bit of crowding happening, and that's a good thing with the hardware sensor development, because more options, the cost will go down. As far as we know, there are no other software players enabling the use of this next gen technology. And the approach we're taking is very different from the deep learning based approach that everyone else is taking. And this presents two opportunities. One, redundancy in the approach we're taking. And then second, redundancy from hardware perspective. So all the players in this AV space are our potential customers. We're enabling technology for them where they can go to market without having to worry, ooh, what happens when I come across a scenario that I haven't prepared my computer for. So this is where, as you know, having a way to address the new scenarios has been holding the industry back from scaling from one part of the city to the rest of the city, or even beyond one city at a time. And we've been there where we've been running a full AV stack, doing a training approach. And that's very expensive from capital perspective and also from time perspective. So that's what motivated us, Joel and I, to start Bluespace with a different approach that will enable us to scale. So that was the long answer. So we're very different, I guess, the short answer. So not crowded, but we're doing it all.
So, and do you feel that your IP portfolio that you're developing is sufficiently differentiated from everything else that you're very confident that you can take that forward and protect yourselves?
Yeah, definitely. We are taking a brand new approach to the perception problem, and our IP portfolio is capturing those ideas and those technologies. And because we're first movers in this space, we are really trying to capture that both here in the US and in global markets.
Okay, and sorry, last question. I know I'm hogging the mic here. What kind of advisory board or people have you got that are working with you to help you push the business forward? Who are your mentors?
Yeah, our mentors are all our investor base and some of the players who've been in the space. Brian McClendon, he was VP at Google, and then he was recruited to Uber to run their AV operations. And I think it's some of the, I guess, learnings from what worked, what didn't work. And we have firsthand experience as well. In our prior company that was spun out of Stanford AI Lab, we actually operated in 2 different cities in Texas, carrying passengers. And I think what we realized was that, hey, deep learning approach is great to getting to 95%, but then figuring out all the different operational aspects and understanding some of the limitations of the previous approach gave us the insight on how do we do this better. But more importantly, we're not trying to be the one operating these services. They're very expensive. And those guys who are looking to operate the fleet or operate a service are ultimately our customers. So whether it's an OEM or fleet operators will really take advantage of our technology and be able to scale because they have the army of sales, global presence that Bluespace as a small company do not have.
All right, Greg, do you have a question?
Yes, I do. This is very interesting. I was trying to imagine one potential space application for your technology is collision avoidance of orbital debris. But that happens very, very fast, and it's hard to see things from all sides. So I didn't know about the reaction ability of your technology, if it would be able to work in the high speed environment of a low Earth orbit of a spacecraft trying to avoid a lot of debris flying in all directions.
Yeah, so our perception software can work at all velocities. There's no real limitation there. The sensor hardware itself may have some some maturing to do in terms of the range and velocity range that it supports to work at orbital type velocities. But I can definitely see near term applications for things like rendezvous and operations around two spacecraft that are meant to be close to each other. And in the future, as the sensitivity improves and detection ranges get longer and longer, we can add on a capability for collision avoidance. Although I guess we then need to also look into the control authority available to the spacecraft itself to get out of the way in the time that it has available.
It's an interesting test case. Thank you.
Chandra, did you have a follow-on?
Yeah, I did. Really innovative, you guys. That I was really impressed with your answers. You can tell we probably have a bit of a background in this. I'm just wondering the cost comparison to regular LiDAR to your system, what you're doing, how it compares, and how you plan to tackle that market if it's quite a bit more expensive, which I think it might be. So
Yeah, so actually the key thing is it's not that much more expensive right now. It's comparable in price to the other, high-end 3D lidars with many, many laser channels. But the key thing is moving forward, because these technologies can be implemented, through silicon photonics and IC like manufacturing processes. Essentially, FMCW approaches require less power, so overall power, since they get better signal to noise ratio, so they can be implemented on silicon on a single chip, as opposed to the existing 3D lidars that have to put out a lot of power through, because they're pulsed. They need to put out a ton of energy to get the return signal back. And because those require like multiple laser diodes and so on, that cost scaling has been slower. And I think over the past 10 years, we've gone from tens of thousands to thousands now. We'll see that scaling happen much faster in the FMCW space, since they can leverage essentially silicon manufacturing as opposed to putting multiple separate components together.
Mm-hmm. And quickly, you might have covered this. You guys have patents on this?
Yeah, on our perception software that leverages this.
Okay, thank you.
All right, Max, did you have a question?
Yeah, I guess I kind of just have a fundamental layman's question. When I'm hearing you guys talk, what I think I hear you saying in some sense is that I don't need to know what you're likely to do in order to see where you're going. I can tell it based on first principles. You're here now, you're going this fast, you're accelerating at this rate. I know where you will be, right? But I'm trying to make sure I'm understanding that, because I do really kind of wonder in some ways. I mean, like, unexpected things happen, right? You can't always extrapolate an acceleration from one to another. There are inherent, like, for example, I believe in one of your graphics, you had somebody on a scooter who was making a turn, and you see some things that are around it, and you say, okay, he's not going to run into the wall, he's going to turn, right? But what if he's in the X Games and he is going to run into the wall? He's going to flip off that wall, and now he's not he's not doing something that's typical. He's not doing something that makes sense, but it's still a situation that has to be dealt with. I'm basically just saying not all motion can be derived from first principles when free will is involved. So I'm curious to know how you guys deal with that.
Yeah, that's a great observation. And I think you are right in that we are trying to get to a first principles approach to the perception problem. Instead of taking the usual like methods that have already been approached, we started from the beginning and said, okay, first principles, what can we measure? What is possible to be measured? And what can we say about these objects' motion? So you're right in that we can't control free will. Everybody can choose their own actions in the future, as much as we may like to try otherwise. But the key thing that we're optimizing for is, okay, you can't control what other people will do or their actions in the future, but we can minimize the latency between when they choose to change that action and when we know about it. So that's why we really have a strong focus on getting that latency down. So getting to what's our motion now and what's our acceleration now. And if they choose to change that, we want to know as soon as physically possible. So yeah, that's really, we're getting down to first principles of let's not assume what people will do. Let's not assume what other agents in the scene will do, but know as soon as physically possible when they choose to do something.
Thank you.
And I may
All
add,
right.
when you do make certain assumptions like that, that's when accidents happen. When the car, we talked about this, when the car goes over the divider and flies at you, cars are not supposed to fly and drive in the wrong direction. And now you need to react to that. So as per Joel's comment, we want to see that change as soon as physically possible and be able to react to it so we can navigate safely here on Earth or in space.
All right. Thank you.